Hello guys, have you ever imagined how stars like our sun were born and die? In upcoming series of videos, I'm going to explain the magical physics behind life and death of stars. So don't miss these videos. This is Parameswaran, your physics yogi. In this video, I'm going to explain the core process which keeps our sun and other stars alive, what we call nuclear fusion. Well, I think everybody watching this video have some basic idea about it. So, in this video, I'm not going to say fusion is the process in which lighter nuclei combine to form heavier ones and blah blah blah. Instead, I'm going to make you feel what the heck really happening during nuclear fusion. To understand fusion in a better manner, first you should have a clear idea about potential energy. According to definition in our books, potential energy is an energy stored in a particle due to its position in space. And if you let the particle free in that position, it will move such a way in space as to reduce its potential energy. This is what book says. Confusing, right? Let me clarify. For our better understanding, let us consider central potential. Here, central potential is nothing but a potential energy due to separation between particles. It depends only on R. In general, most of the potential we experience in our day-to-day life are central potential. The gravitational potential, electrostatic potential are some examples of central potentials. For our simplicity, let us consider positive charge, whose central potential graph as a function of R looks like this. Now, if I place another positive charge here, what will going to happen? Due to the influence of the charge, it gains some potential energy, right? For our understanding, let us say it gains a potential energy of 10 electron volt. Now, if I let that charge free, what will happen? Slowly converting its potential energy into kinetic energy, it starts moving from higher potential region to lower potential region, right? This is because we know that everything in our universe wants to be at as minimum potential as possible. So wherever if you place this positive charge, it always moves to lower potential. In our case, it moves to infinity. Now, as it approaches infinity, potential energy of the charge becomes zero and kinetic energy becomes exactly equal to its initial potential energy because total energy has to be conserved, right? Similarly, from infinity, if I send a positive charge with a kinetic energy of 10 electron volt towards this charge, what will happen? As the distance between these two charges getting smaller and smaller, approaching charge kinetic energy will slowly decrease by increasing its potential energy, right? So, due to this reason, the approaching charge velocity will decrease, and when it approaches R0, its kinetic energy becomes 0 and potential energy becomes 10 electron volt. At this instant, the charge stops and reverses its direction. It will not move further inward because total energy has to be conserved, right? So, it again moves to infinity. Likewise, from infinity, if the approaching charge initial kinetic energy is greater than 10 electron volt means it will approach little bit closer. So, the greater the initial kinetic energy of that approaching charge, closer it will approach. Hence, from this example, I think you get a clear idea about what is potential energy and how particles behave in central potential. With this, I think we can dive into our topic. Let us consider two nucleons separated by a distance of few femtometers. Most of us thinking that strong nuclear force is always attractive. If this is true, over the course of time, these two nucleons will merge into one. But in reality, nucleons will not merge, right? They just stick together. So, some kind of repulsive force at smaller distance stopping them from merging. To understand this, let us plot a graph of strong nuclear force between these nucleons. By seeing this plot, I think you grasp my point. Below 0.8 femtometers, nuclear force become repulsive. In between 0.8 to 3 femtometers, it acts as attractive, and above that, it completely becomes zero. Hence, we can say that nuclear force is the resultant sum of both attractive and repulsive force. This is the reason why nucleons do not merge. Now, if you look at this nuclear force graph closely in this region, it looks familiar to us. Can you guess it? Yeah, it looks like a harmonic oscillator force, F equal to minus kx. So, if you place nucleons within a distance of 1 femtometer, they behave like a harmonic oscillator. They will exhibit oscillation about their mean position or not. Hence, by seeing this, fusing nucleons seems very easy, right? Just if you send a nucleon in the direction of another one, when the distance between them becomes few femtometers, the attractive nuclear force will take over and bound them. Very easy, right? This is what most of us think. But physics here is much more complicated than what you think. To understand what exactly happening here, let us consider potential energy associated with this nuclear force. Now, from 100 femtometers, if I send another nucleon with a kinetic energy of 1 kilo electron volt towards this nucleon, what exactly will happen? Initially, the approaching nucleon does not feel any nuclear potential, right? Because it is too far away, so it approaches with constant kinetic energy until it reaches 3 femtometer. As it gets near 3 femtometer, it starts to feel attractive nuclear potential. By this reason, it gains kinetic energy and starts falling from higher potential to lower potential. As it reaches R0, its potential energy become minimum and kinetic energy become maximum. Due to this maximum kinetic energy, it again starts to move inward until it reaches R1. At this instance, its kinetic energy becomes 0 and potential energy become exactly equal to total energy. By this reason, the nucleon stops and reverses its direction. It will not move further inward because total energy has to be conserved, right? So, it moves backwards. Now, again, as it approaches 3 femtometer, its potential energy becomes 0 and kinetic energy becomes exactly equal to its initial kinetic energy. Hence, due to this reason, it moves to infinity without getting bound. From this, we can conclude that approaching nucleon will not get bound if it has some initial kinetic energy. So, only way to bound this nucleon is by placing it within a distance of 3 femtometer with 0 initial kinetic energy. Practically, it is impossible, right? But in reality, some kind of fusion is taking place. So, this can be achieved only if some kind of energy loss occurs during their interaction time in the form of radiation. The process looks simply like this. As the approaching nucleon gets very close, due to weak interaction between them, it will emit most of its energy in the form of beta radiation. By this reason, its total energy gets decreased and it becomes bound. This is how initially two nucleon fusion take place. Note that we cannot have that initial two nucleon fusion without beta decay. So, weak nuclear interaction plays an important role in nuclear fusion. Without this force, our known universe would not exist. You will see this shortly in my next video. Here, in this video, for our understanding, I just fixed one nucleon in the origin. But in reality, two nucleons will approach each other, right? So, this is how two nucleon fusion looks like in reality. What I discussed in this video is only applicable to proton-neutron and neutron-neutron fusion. Can you guess why? Leave it in the comment box. Similarly, what I discussed in this video is only for your intuition purpose. It will not have physical significance because free neutron is unstable, right? It will decay into proton within 15 minutes. So due to lack of free neutron, naturally proton-neutron and neutron-neutron reaction will not occur. The only possible reaction is the proton-proton reaction, which I will discuss in my next video. So the main motto of this video is to give you intuition about how nucleons behave in nuclear potential and weak nuclear force behind fusion. Thank you so much for watching this video. Please like and subscribe to my channel for future video notification. It took 3 weeks for me to prepare this video, but it takes few seconds for you to share with your friends. If you like this video, please share with your friends and support me.